All right, so this is picking up where the previous presentation left off, the end of the positive description of Popper's method of falsificationism and his justification for it. So remember that he had just these two kinds of hypotheses, those that have been falsified and those that have not been falsified, and he arose at this because he thought that what scientists should be doing, the proper way of conducting science, is to try to prove that things are false, that there is no scientifically proper method for trying to show that things are true, or even that they're more likely to be true, or that you're sort of on the right track towards truth. He rejected all of that sort of inductive reasoning that would go on in science and thought we should just be trying to prove things false. So you see there's nothing about truth here in these two categories of hypotheses. Okay, so now we're going to look at the primary problem with Popper's suggestion here. There are a few others that I won't get to. You can take a philosophy of science class maybe and get to some of the other problems. But here's his main thing. Remember, here's his method of falsificationism. It's just modus tollens. If H, then I. The second premise tells us not I, so therefore not H. Looks like you just proved that the hypothesis is false. But while this is indeed a deductively valid argument form, we know that it's modus tollens, but it turns out it's not deductively sound, in particular that first premise. So that first premise is, in a way, it's false. It's false because it's just not an accurate representation of the actual experimental situation. It just cannot be simply, if the hypothesis is true, then the test implication is true, the prediction will be true. It's just not as simple as that. And the reason it's not as simple is because actual scientific experimentation requires very careful planning and setup and execution of the experiment. And so it involves all of these things that we call auxiliary assumptions. So the auxiliary assumptions are all of the various aspects of your experiment that you assume are going true, right? That you assume are true, or that are going according to plan, so that the results you get are reliable results, so that you can use them to really evaluate whether you are on the right track or not with your hypothesis. So here's a few simple examples. Right? So you assume that all of the equipment that you're using is functioning properly, that you've calibrated it properly, that you're using that equipment properly, so that you're following the procedures correctly, and that you have a procedure that is a good procedure right from the very beginning, that you're not missing some step in a major way that's going to cause the results you get to not be very reliable or not relate to the quality of your hypothesis in the way that you would want it to. That your test materials are unspoiled, right? So if you're doing some, say, a chemistry experiment that requires that you dissolve your sample in acetone, well, are you sure that the acetone that you're using is uncontaminated? Because that contamination could throw off your results. How do you know your acetone is uncontaminated? Maybe you're mixing this together in some glassware into a glass beaker or something. Did you wash that beaker? Are you sure you washed it properly? Are you sure that there's no leftover contaminants inside that beaker that are going to throw off your results? Hopefully, if you're a good sort of experimentalist, then you washed your glassware properly, but that's an auxiliary assumption. You assume that it's true, that the glassware is clean enough to be used and to be giving you good results by using this glassware. And then, there's lots and lots of other things we could talk about as far as auxiliary assumptions, but then there's this big sort of vague category of auxiliary assumption. You assume that there's nothing unknown that's messing with your results, that's interfering with your experiment in some way. Or you assume that, even if something is known, that it's not influencing your experiment in some unexpected way. And this seems so vague, like why do we have to keep track of this? Well, there's lots and lots of examples from the history of science and contemporary like science that's going on now, where something unexpected was influencing the results. Something, maybe it was this unknown influence, especially, examples in fundamental physics. They're doing all these experiments and it's just not coming out the way they expect. Well, that might hint that there's this unknown thing, this new force of nature, something brand new that's screwing up their expected results. Or just something that is known, but they didn't expect it to influence this experiment in the way that it actually does. And so it could take years, decades in some cases, to identify what auxiliary assumption turned out to be wrong. So if we were to rewrite Popper's method of falsificationism here, it would look something more like this. So if the hypothesis is true and all the auxiliary assumptions are true, if that whole antecedent, that conjunction in the antecedent is true, then the test implication would work out as expected. Then if the test implication does not work out, right, so the test implication is false, then what? Well, that whole conjunction that's in the antecedent in the first premise, that whole conjunction is false. It's false that the hypothesis and all the auxiliary assumptions are true. Here's another way of writing it out. If the hypothesis is true and auxiliary assumption number 1 is true, and auxiliary assumption number 2 is true, and auxiliary assumption number 3 is true, how many do we have to list? All of them, right? And there could be dozens or hundreds, or in the case of actual scientific research, like if you go into one of the high-end laboratories on CU's campus and start looking at all of their equipment and their experimental procedure, there could be thousands of auxiliary assumptions that all need to be working out as expected, right? All those assumptions need to be true in order for them to be getting reliable results from their experiment. So if the experiment does not turn out as expected, that is, the test implication turns out to be false, then what? Right? One of those things in that conjunct in the first premise is false. Either the hypothesis is false, or auxiliary assumption number 1 is false, or auxiliary assumption number 2 is false, or auxiliary assumption number 3 is false, or some combination of auxiliary assumptions is false. They're just, in the problem, if it's not already obvious, is that there's no deductively valid procedure that's going to point us in the direction of exactly which of the auxiliary assumptions is the one that's false. And so if the prediction fails, then a good scientist, rather than just immediately jumping to rejecting their hypothesis, a good scientist will first check all of their auxiliary assumptions as best they can to see if one of those turned out to be false in some relatively straightforward way. How do you check all those auxiliary assumptions? You need to test them. And so you're right back into this process of testing again. And so you're gaining evidence in favor of the auxiliary assumption being true, or evidence in favor of the auxiliary assumption being false. And that's back to induction. So although Popper wanted us to completely abandon using induction and stick to this strictly deductively valid method of modus tollens in science, which he called falsificationism, it just can't work out. The real scientific situation just does not allow that to really happen. So here's an example, again, another really excellent example that everybody in the scientific community would recognize as being a good example of science, but it actually is a radical violation of Popper's suggestions. So back in the early 1800s, people were aware of all of the planets out to Uranus. And they had been using Newtonian theory to guide their exploration of astronomy. But then when they started to track Uranus's orbit, they noticed that the actual observed orbit was deviating from the calculated orbit based on Newtonian theory. So if Newtonian theory is correct, then the orbit should be this way, a certain way. The orbit was not that way. So according to falsificationism, they should have rejected Newtonian theory back in the early 1800s. But they didn't, right? What did they do? They started looking at auxiliary assumptions. Once they made sure that their observations checked out, right? There's nothing wrong with their telescopes or their mathematical techniques that they were using to calculate the orbit. And once they figured that was working out okay, then they made this sort of crazy guess. Maybe there's like some other planet that nobody's ever seen or heard of or even suggested. Maybe there's this other planet that's out there further away than Uranus, and the gravity from that other planet is tugging on Uranus in just the right way to cause this deviation from what's predicted. completely ad hoc, right? Just out of nowhere. You've got this evidence against your favorite theory, Newtonian theory, and so rather than just rejecting the theory, you come up with this brand new thing to try to explain away the evidence. Well, it turned out that this is a testable ad hoc suggestion. So they ran through the calculations and said, well, if there is this other planet that exists that's pulling on Uranus in just the right way to cause the deviation from what's expected, then that planet should be right about there in the sky. So they turned their telescopes to that point in the sky and they found Neptune. So they actually discovered a major gas giant through this method by checking the auxiliary assumptions rather than just abandoning the Newtonian theory because of this one negative result. And if it's not obvious, one of the auxiliary assumptions was there aren't any other big planets that have a gravity strong enough to be pulling on Uranus and causing it to deviate from the Newtonian prediction. Well, it turned out that assumption was false, and they did the work and figured it out. So this is all just sort of to evidence, right? Reasons for thinking that Popper's method is just way too strict. You can't use deductive logic, the deductive method of modus tollens in a straightforward way in science like that. It's just too messy. There's too many auxiliary assumptions to keep track of. And showing that those auxiliary assumptions are true or that those auxiliary assumptions are false, it's gathering evidence in favor or against those. And so whether you're sort of getting evidence against a hypothesis or you're getting evidence in favor of a hypothesis, either way, it turns out that it's induction, right? You're gathering evidence that makes it likely your hypothesis is true, or it makes it likely your hypothesis is false, but in both cases, it's not definitive. You're not getting 100% guaranteed proof that the hypothesis is false, or, of course, we already knew this, that you're not getting 100% guaranteed proof that the hypothesis is true either. It doesn't work either direction. So we're stuck with induction and doing the best we can. Here's a couple of other examples if the point's not obvious. An introductory chemistry student, you're doing laboratory exercise in your introductory lab class, and you're following the procedure as it's written out for you, and it says that by the end of this procedure, the liquid in your test tube should turn blue. So let's say you run through the procedure and the liquid in your test tube is not blue. Well, according to Popper, you just falsified chemistry, right? This introductory lab exercise is almost certainly based on something sort of fundamental, some basic fundamental thing about chemistry, chemical theory. So did you just falsify chemistry? Like, no, that's silly. The chances are much better that one of the auxiliary assumptions is false. It's false that you followed the procedure correctly. It's false that your glassware was cleaned properly, or maybe it's false that the chemicals you're using are purified properly. There could be a contaminant in there, or one of dozens of other possibilities. Then a really high-end example of physics, the Large Hadron Collider. This is, without exaggeration, in all likelihood, the most complicated thing humans have ever built. And so we're talking literally millions of details that they need to keep track of to make sure that they're getting good results from this thing. They weren't going to spend whatever it was, $50 billion building this thing, run it once, get a negative result, say like, oh, that just falsified the whole theory that this machine was based on, let's move on. Of course, science doesn't work that way. Of course, they look at all the auxiliary assumptions. In fact, they spent years just doing test runs and making sure all their auxiliary assumptions were working out as expected before they ever gathered any evidence that they felt was reliable. In the Eddington expedition, Popper portrayed that as like they found one observation, right? The star was displaced in the sky from our perspective, so that meant that the light bent as it went through the strong gravitational field of the sun. So that was taken as proof that Newtonian theory is false. Well, you look at the history of how the scientific community reacted, and they didn't just immediately flip like that. There was a long and very reasonable discussion about the quality of this evidence and all the auxiliary assumptions and so on, and it took time, right, and lots of other evidence in favor of Einstein's theory and against Newton's theory before the scientific community was really willing to start to shift over to shift over to Einstein's theory and away from Newton. So In reality, scientists just don't really follow Popper's strict method of falsificationism, even when they say they are following it, right? Even when they claim to be Popperians, or they accuse their rivals of not being Popperians. Turns out none of these guys are, or women, right? None of these scientists are Popperians. It just isn't the case. But there is something that we should take from Popper, right? He was correct about something, that it is important to look for evidence against your theory. If all you're doing is trying to support your theory, then you might indeed be drifting off towards something like pseudoscience. We shouldn't go so far as to say that when you get one piece of negative evidence that proves that your hypothesis or your theory or whatever is false, that was too much. But just this basic idea that we should do both, right? We should be perhaps looking for evidence in favor, but we should also pay very close attention to looking for evidence against our theories. That's important. And that if somebody provides us with a theory or a hypothesis that's truly unfalsifiable, right? That there's no possibility of any evidence that could ever count against it, well, that's probably not a scientific theory that's worth testing, that's worth pursuing, right? It's kind of untestable because it's impossible to find anything that could ever count against it. We should be very skeptical about those kinds of theories. So Popper had some good ideas, but we don't want to carry it as far as he did. Okay, so back to this. This was one of the things at the very beginning of the last presentation. Here are the two big questions we're looking at, right? What form of logic is involved? Well, induction, right? Deduction, at least in this aspect of scientific reasoning, just it's not possible. The world is just too messy and complex of a place for it to be possible for us to use this simple method of modus tollens to start proving things false in this systematic way. So on to the next thing. So when scientists are providing us with conclusions, causal explanations, how do we go about judging the quality of those conclusions? Well, this is something that we talked about a little bit already. So this is from the book, and we used the Semmelweis example to point this out, the method of agreement, where all the examples of some effect happening, what do those examples have in common? And it turned out, in the Semmelweis example, all the deaths had in common that it was the medical students that were introducing accidentally, unintentionally, introducing the cadaveric material, the dead tissue into these women who were giving birth, and that was killing them. So that was the thing that agreed between all the different examples of the women who died. They all were treated by the medical students who had just done autopsies. Then there's the inverse method, right? You take away what you think is the causal connection there, right? The common thing that's happening to all the, in this case, to all the women who are dying, take it away. So you wash your hands so that the cadaveric material is not introduced. And the effect, the death, goes away. So these are some pretty straightforward methods. If scientists are doing this, then good. But even better is the modern examples of this kind of testing. And we see it often when they're testing some new medication for some disease. So ideally, they would want to have a control group and an experimental group, right? So the control group is a group that's been selected. So the sample from the larger population has been selected in a good way. We saw that earlier in chapter 10 about what are the things you need to keep track of to make sure you've got a good sample of the overall population, and in order to make sure that when you study the sample, you're getting sort of something reliable that you can apply to the whole. So you do that twice at least, right? You get one that's a control group and one that's an experimental group. The control group you do nothing to see sort of what's your baseline effect, like what's this sample gonna do? How's it gonna behave? What effects are we gonna see with that sample if we do nothing to it? Versus the experimental group. This is where we do introduce what we suspect is the causal factor and see how that affects them. And now we've got a basis of comparison. We can compare the experimental group to what's happening to the control group. And as long as the only thing that's different between those two groups is this one thing, like this one medication, then we'll know that the difference between the groups is due to that one thing. It's due to the medication. The other thing that they do is something you may have heard of, this double-blind procedure, where the people in the groups, they don't know if they're in the control group or the experimental group. In fact, the control group will be given something that seems like a medication, you know, a fake pill or a fake injection or wherever it's administered. So they don't know if they're getting the medication or not. Because remember, the only thing you want to be different between these two groups is one gets the medication, the other doesn't. You don't want it also to be the case that it's different about what the group members know. You know, if the people in the control group know that they didn't get the medication, well, that itself, that knowledge is a difference between the control group and the experimental group. And you don't want that knowledge to be playing a role. Also, the people that are administering the medication, they don't know who's in the control group and who's in the experimental group. So as they're giving people the pill or giving people the injection, they don't know if they're giving sort of the fake drug, the placebo, or the real drug, or the real medication. Because they might influence, they might give some subtle cues to the person they're giving the medication to as to whether this is the real thing or not. And you don't want that psychological influence to play a role. Then finally, the people that are evaluating the groups to see if they're getting sick or they're getting more healthy or whatever the medication is intended to do, the people that are studying the effects on the groups, they don't know who's in the control group and who's in the experimental group, because that kind of knowledge can subtly influence how they evaluate the patients that are getting in one group or the other. And then you want the groups to be as big as possible. You want the groups to be representative of the whole population. You want to repeat this experiment over and over again as many times as you can. This gives you the statistical robustness so that you can have a lot of confidence that what you figured out is happening to these samples, the control group and the experimental group. What you learned about that can be applied to the whole population. And these lessons about sample groups that we learned about in section 10.2, those obviously apply, right? You need to have a good sample, a large enough sample, one that's representative of the whole population, then it's worth doing. Okay, another thing that they talk about in this chapter, section 10.3 here, about scientific reasoning, is how do scientists accept a hypothesis to begin with? What are they looking for in a hypothesis before they even begin considering it or testing it? Or if they have rival hypotheses or rival theories, how do they decide between these two? Well, some of it's obvious, some of it maybe not so obvious. Some of it they talk about in the book, and some of it they don't talk about in the book. So I'm going to focus on some that they do talk about in the book. That's these ones that are in slightly larger font here. But all of these things are things that scientists are looking at for their hypotheses to do or to be. Obviously, you want your hypotheses to have predictive success. And so here's a little more detail on that. Obviously, like that's accurately predicting new phenomena, right? So they make a prediction, and then when they run the tests or do the observations or the results of the test match the prediction. That's predictive success. Pretty straightforward. But something else to say about this is if what's being predicted is something that's already known, well, that's not a very impressive thing to predict, right? Like I had before, Newtonian theory or any theory of gravity predicts that when I drop this pen, it'll drop down. It's like, okay, but if you're presenting that as a prediction of gravitational theory today, it's like, okay, well, when the pen drops, I'm not very impressed, right? I'm not going to be impressed and say like, wow, that's really great evidence in favor of your new theory of gravity, because we already knew that pens would drop. What we want is something unexpected, something new that this new theory or new hypothesis predicts that wasn't known before, that we haven't observed before. Then, if that prediction does turn out to be true, we'll be surprised and we'll be like, oh wow, now that's impressive. Maybe this new theory is onto something new that we should be paying attention to. This is very similar to what I've just said, but any new theory or new hypothesis that comes along does have to accommodate what's already known. So that in addition to predicting something new and exciting, it also needs to match what's already established. If you come up with some new theory that's a radical departure, right? What this new theory is telling us, or what predictions it's providing, is radically different from what we know is the case. Well, that would give us some reasons to be skeptical of this new theory. It doesn't prove that it's wrong, but it sort of raises some red flags, and we might be worried about it. So it might also want to give us some practical applications, maybe some new technology or something. So overlapping with that predictive success is these two. I'm going to put them together here. The new theory, or any theory or hypothesis somebody comes up with, it's got to be consistent and compatible. That is, it's got to be internally consistent. It can't have any internal contradictions. If it does, then that's a good reason for just being very skeptical about it in the first place. But we have to be careful about that even. The new theory, it's not so new anymore, but quantum mechanics, it contains some things, some understanding that seems contradictory. You know, that something like a bit of light, a photon, can be both a wave and a particle at the same time. That sounds contradictory. But when you work through the theory, it actually works out and became acceptable. But by and large, we don't want our theories to contain weird internal contradictions like that. The other thing, a new hypothesis or new theory or something, it needs to line up with other well-established areas of science. It doesn't contradict something that's already known, and I mentioned that kind of on the last slide. That doesn't mean that the new theory or the new hypothesis automatically is wrong. It just gives us extra reason for being skeptical about it, and that we're going to need some really good surprising evidence and reasons in favor of that new theory or hypothesis in order to accept it. And this is especially true if what's being contradicted is something fundamental, right? So my new theory of psychology, let's say, violates basic physics. Well, then chances are my new theory in psychology is the thing that's wrong. Oh yeah, another thing that to mention is, and I've been saying this kind of a lot in this section of the course, science is in the business of providing causal explanations. Notice that doesn't say casual explanation. It's a very common typo. This is a causal explanation. The explanations need to be based on causation. We need to know, ideally, what scientists are really trying to do is give a full explanation that lays out exactly the details. What's the step-by-step causal details that lead from the beginning to the thing that we're interested in, right? To the phenomenon, to the result. As much as possible, we don't want scientists to treat things as black boxes. And so to treat something as a black box means you know what the input is and you know what the output is, but you don't know anything about sort of the causal details of what happens in between the input and the output. In all honesty, I treat my computer largely as a black box. I'm not a computer scientist. I'm not an electrical engineer. I have only the vaguest notion of what goes on. Right? I press a button on the keyboard, something shows up on the screen. What happens between the button and the screen? It's a black box as far as I'm concerned. But if you're a computer scientist or you're an electrical engineer, it is your job to know what are those causal details all the way through. You cannot treat something like a computer as a black box. If somebody asks you, how does a computer work? It would be lame for the computer scientist to say, oh, you press a button and something shows up on the screen. That's how computers work. Like, no, you gotta give me the causal details. You need the full causal explanation. And then in general, it's better the more a theory or a hypothesis or something can describe, or the more that it accounts for, the better. You know, you can have some kind of a scientific hypothesis or theory on some very narrow, some like individual little phenomenon, but the more that it can explain, the more that it can apply to, the better. And so the best example ever actually was Newtonian theory. One of the reasons why Newtonian theory was accepted is because it explained so much under one theory. Okay, as I've said before, I could just go on and on about this stuff. There's so much to say about scientific reasoning and the quality of scientific arguments and explanations. But let's go ahead and stop it there. It at least covers most of the highlights that are in the chapter on this topic.